All right. Determine IM. So determinants, they're a great topic. I really love it in terms of the geometry. So I kind of want to introduce a little bit of that with you guys. But it's not going to be too rigorous to really get into it. You need higher math, and once you kind of see how a lot of these higher differential geometry type structures work out, determinants become really interesting. So maybe I'll kind of just talk a little bit about it because I would like you to kind of have an intuitive sense of what a determinant is doing and what we are measuring with determinants. But the most important part of determinants for this class is going to be the computation. Do you know how to compute a determinant? And so the computation, very algorithmic, but I do want to kind of at least hint at some of the underlying geometry that is going on and why the algorithm is what it is. And hopefully you'll be able to make sense of that. Okay, so let's suppose we have two vectors. Let's start off, let me try to use different colors too. So we've got one vector. This is going to be the vector AB. So it's essentially a coordinate vector pointing at coordinates AB. And the other one's going to be pointing at CD. And we've mentioned in the past how if I have two vectors that are linearly independent, so right now let's just work at arc2, two-dimensional plane. And if we have two vectors that are linearly independent, then they form a basis for the plane. And you should think of a basis for the plane in some sense as the way we're defining the grid on the plane. That we're going to describe all vectors in regards to linear combinations with respect to this basis. So what we can do is draw our grid lines parallel to any given basis vector, so to our two basis vectors. And we can kind of see, aside from my, let me try to get them as parallel as I can. And if your drawing skills are good enough and you can draw your grid lines parallel, and so our next grid line might be somewhere down here for that guy, and then of course we'll have more of these slanted grid lines. So rather than the typical XY coordinate plane, now we have, let's call this U and V. Vector U and vector V. So we have like a UV coordinate plane. And any point in the plane, whether we're here or here, I can go a certain multiple of V and then add on, walk in the direction of U now, a certain multiple of V of U, and we can get to any point in the plane. So the grid of just are, of course, our integer multiples, but we can go, 1.5 in the direction of V and then half a direction in U, and we end up right here. And so while this coordinate might have certain XY coordinates, we can describe the linear combination of U and V that it takes to get into that point as what might be like UV coordinates. So we are rescaling and regridding our plane or our space, our R3, R4, so however many dimensions we have and however many basis vectors we have. This is kind of what you want to think of as a basis doing. And so what we want to do is measure in some sense our unit area. So for those of you who've had calculus, Calc 1 and 2 even, you measure things in terms of like our dx. Our dx is kind of like the unit length that we're measuring along the x-axis. And in Calc 3, you start to do multiple integrals, dx, dy. And hopefully, if you've had all of Calc 3, then you've done changes of coordinates. So you've actually seen a lot more of this in even more complex settings in Calc 3, because you'll go from, excuse me, if you go, for example, from our normal Cartesian coordinates, our xy coordinates, into polar coordinates, it's doing something very similar. And what happens if we change to polar coordinates? What happens to our area differentials? So maybe we write some of this down. So in calculus, we have this area differential. Right? If I want to find the area of some space bounded between curves, we usually do an integral of dA, or in rectilinear coordinates, it ends up being dx times dy. But what happens when we change it to polar? You get RD theta. So the area differential isn't linear anymore. It's not just dr d theta. We have to actually scale it now. The area differential that we're using, so in some sense, the grid lines that we are using in the area that's created by the grid lines, is going to change with the radius, with the distance we are from the origin. Nicely enough, in linear algebra, we don't actually have to worry about these functions. So this is also called the Jacobian. If you've had Calc 3, you get into even more complicated change of variables, and you just need your change of variables to be differential. So the grid lines aren't even straight. You can have curved grid lines. Of course, polar coordinates has curved grid lines. But in linear algebra, everything is linear. Everything's a straight line. Everything is flat. So our grid lines are all the same size. I.e. the same scaling factor. And, of course, they're straight. So we don't have curved grid lines. We don't have our area differential changing based on some function. In other words, our dA, let's say if we had our xy coordinates, is going to be the same thing as the area differential using our new grid lines of u and v, but maybe just times a constant. So you can kind of see from the picture exactly what's happening. Well, they're straight lines, straight grid lines. And of course, what's going to happen when we have straight parallel grid lines? Well, they form nice parallelograms for our unit intervals within that system of measurement. And we know how to compute areas of parallelograms. That's not too hard. And so this is what's going to lead us to the determinant. So we won't, of course, be doing any sort of integration and won't have to worry about area differentials necessarily. But that's kind of the idea you want to think of. You want to think of it in terms of like, how are we measuring the space? What does our grid look like? And so with a different basis, or even just some subset of vectors, we want to measure the volume of the parallelogram. And in higher dimensions, this is called a parallelepiped. That they form. So this is our 2 unit vectors. And we can kind of see if we just start with those 2 vectors and make this first parallelogram out of them. This parallelogram defines how the grid is going to look. The grid is formed by tiling this, right? We just take the same parallelogram and keep copying it and move it around different locations. And that gives us the grid. So we want to know, well, what is the area of this? Is it a different area? Our x times y, of course, has a unit 1. Every box, 1 unit area. And so we can kind of understand volumes based off of linear combinations of I and j of our standard basis vectors. So if we want to understand now volumes in terms of linear combinations of u and v, well, we want to understand, well, what is the area that they span in their parallelepiped? And this is what determinant is going to be. So let's go through the computation. So how do we compute this? So let me try to redraw these. There's a couple ways we could go about doing this. And I think I'm going to do it the easy way, but maybe I'll leave it to you to double check our formula. So the way we're going to do this is we're going to build this up. We're going to start in 2 dimensions, figure out the formula for determinants in 2 dimensions. Then maybe we'll talk about what's going on in 3 dimensions. And then we'll generalize that and just give the formula for higher dimensions. And it'll be a little hand wavy since this is a non-rigorous math major course. But hopefully through the hand wavy, you'll get the geometric picture of what's going on. And that's really, in my opinion, what's important. As long as you know how to do the calculations, that's pretty easy. And then at least have a vague notion of like why we're arriving at that formula. So this vector, let's put it in a column vector, has AB coordinates. And then our orange one had CD. Now, what is our area of a parallelogram? Well, base times height, where we can choose base as any side. And the height is a perpendicular to the base. So again, let's call this guy our U. Let's call this guy our V. So if we take the length of U equal to our base, so our U is going to be our base. The length of u, of course, will give us the size of the base. The question then is, well, how do we find the height? So maybe I should have made that a different color. Let's make the height green. Or I guess it'll just stay red. Can't really tell the difference on the video. So how do we find that? Well, there's a couple things to do. So I'll give you the hard way is the homework assignment. It's not hard though. We know that h is going to be the length of v times sine theta Well, how do we figure out what sine theta is? We do know at least that u dot v gives us a notion of cosine theta. Meaning we can find cosine of theta is u dot v over norm u times norm v. Well, what does that mean? That means theta is going to have trig ratios that look like this. If you think way back to pre-calc when you first learned this, and I know you learned all of this or used all of it, a lot in calculus, a lot in calc 2 doing trig subs. If I know cosine of theta has a ratio of u dot v over norm u norm v, we can actually figure out the length of this third side of a triangle by taking the difference square. So this is going to be norm u squared, norm v squared, minus u dot v squared, all under a square root. And so we can compute now that our area is going to be norm of v, norm of u, norm of v, sine theta, which is going to be now, I'm just going to write it as sine theta, but it'll be opposite this term divided by the hypotenuse. So the square root term divided by norm u, norm v. And so nicely enough, the norm u, norm v are going to cancel off. And so you'll have the area is actually just going to be determined by what's underneath this square root, or determined by this square root. Write everything out in terms of your A's and B's of what the norm means and what the dot product means, and simplify. So check that and see what you get. So just make your substitutions, spell out what the norms mean in terms of the coordinates, spell out what the dot product means in terms of the coordinates, and you will derive the formula for the area. And this is going to be the area or the determinant of our matrix. Let's go about it a different way. Let's use a little bit more of our advanced techniques. This is a kind of advanced. We're using our dot product. But let's use our linear algebra skills in terms of our understanding of parallel vectors and dot products and projections, namely. So what is this h? Well, this h is a perpendicular. It's perpendicular to u. So really, if we wanted to plot h as a vector, it would go somewhere along this direction. And we were talking earlier about in this semester when we got into orthogonal vectors. If I have a vector u, and this only works in 2 dimensions, there's ways we can generalize this method to higher dimensions. So maybe we'll touch base on those once we get to higher dimensional determinants. I don't think they're necessary to use. The book uses them. But sometimes you get too technical with some of these processes and it almost convolutes the process itself and the way of going about solving problems. But nicely enough, in 2 dimensions, this works well in the sense that there's a unique perpendicular vector that we have formed based on u, up to direction, I guess. Namely, if I want a vector that is perpendicular to u with the same size as u, what did we have to do? You guys remember? So let's see if we make that maybe a little too big. How do we create a perpendicular to a 2-dimensional vector? We simply flip the coordinates and then we make one of them negative. So the one I've drawn, the b term, is negative. If we wanted to flip the direction, if we changed our negative, it would just be down here. So it's still going to be BA, but this one, the A is negative. And so what is H? How do we find H? H is the projection of V onto this perpendicular of U. So let's call this green vector U perp. Right? If we just take, we really what we want to break V down in terms of this component in the perpendicular direction of U, and then the component parallel. And we can ignore the parallel component because that doesn't contribute any more to the height. So this is going to be our H here. Well, how do we find this? This is just our dot products. So this is going to be U perpendicular dot V over the norm of U perpendicular. And actually, if we want to square that and write it in the direction of our perpendicular vector. So that was our formula for our projection. Now keep in mind this projection actually gives me the vector. So if we solve this out, it would give me the vector for H. If we are just talking in terms of pure area, we would want to take the length of that. So if we take the norm of everything, what are we going to get? Well, u dot v is a scalar. Sorry, u perpendicular dot v. And then it'll give us the norm of u perp over 2 products of u perpendicular. So all in all, the length is going to be reduced a little bit to just the dot product u perpendicular dot v divided by the length of u perpendicular. Okay, well, u was the base. So now our area is just going to be u perpendicular dot v over the length of u perpendicular times the length of u. And so if we fill in our pieces, let's go ahead and do that. So our u perpendicular dot v, well, we're taking a dot product of minus b a dot cd. And so we're going to get BC, negative BC. So I'm going to write it as AD minus BC. And then what's special about the, well, norm u and norm perpendicular of u are going to be the same, right? Norm of u is just going to be square root of a squared plus b squared. Norm of u perpendicular is going to be negative b, but when we square it, that negative is going to go away, plus a squared. So since those two are the same, our area is just going to be the absolute value of the dot product of v with the perpendicular vector of u, and that's going to give us AD minus BC in absolute value. So this term is what we call the determinant. Maybe my notation is a bit bad. Let's call these, actually write these out. We don't want to use the same letter to mean different things. I've been using A for areas, but we've also been using A a lot this course to mean a matrix. Actually, they're not terribly different in terms of linear algebra. So this I'm going to call the determinant of A, where A is our matrix formed by the vectors u and v. So we commonly write, so here's going to be, I'm going to write it as theorem proposition / definition. So for a 2x2 matrix, they commonly switch the B and C, so you should note that if we take a transpose, it'll simply look like that. The formula ends up being the same, and of course we'll arrive at that this lecture, hopefully, that we can take transposes, and the determinant of a transpose isn't going to change anything. We define the determinant of A by, sometimes we write out the word det of A. Sometimes you simply write the same matrix, but you put absolute values, or instead of like a square bracket, it's just a straight line. So think of it like an absolute value, which is really what we've been doing, right? We want to know the absolute area of it. And so what do? We just take the product of the diagonals and we take the difference. AD minus BC. Now, notice here, this one, we usually don't keep the absolute values in just a pure determinant. So this is our definition. The actual theorem of that is that determinant of A gives the signed, so that's just going to be a plus or minus area of the parallelogram formed by the column or row vectors of A. And that's essentially what we just deduced with our picture and our geometric work. So of course you can kind of think of this one, A, really all we did was take those same vectors. Now we just put them in rows. And we've mentioned this a little bit. I know we haven't worked a whole lot in this class, but you can really kind of think of matrices, whether it's a column vector or a row vector, they both very much work in the same way. We've seen at least how we can define the rank in terms of the number of linearly independent column vectors, which is also going to be the same as the number of linearly independent row vectors. We've done a little bit of work with elementary matrices in the first week. So far, all of our elementary matrices correspond to row operations. We've done a lot of row operations with a lot of our procedures, but you can also, if you wanted to, turn those into column operations. And those would actually correspond with elementary matrices acting on the right. So all of that information is kind of stored within the matrix, and it kind of doesn't matter whether you're using rows versus columns. The information is all kind of there and all means the same thing geometrically. The difference between rows and columns really is just kind of like how are we organizing that information. And luckily enough, as long as we're consistent, it doesn't matter whether you want to use rows or columns. We get the same results. So why do I say signed area? So what is going on here? Well, the way we have it and the way we solved it, I took V as the projection onto this vector, but I was nice to myself in this drawing. My V was coming up here, my U was coming up here. Both were in the first quadrant. I could have had one V down in the third quadrant. U could have been in the second quadrant. So the directions of U and V could be different. And so in our area computations, we kept the absolute values to determine the length because that's what we cared about in terms of the area. But as you can kind of see in the formula we derived, that if we didn't keep track of those absolute values, if we kind of just lost those absolute values a little bit and used our pure vector notation, well, sometimes when you take dot products, this quantity could end up being negative. And that's actually kind of good for us. We've seen in linear algebra how we're building on some of these basic mathematical tools of functions, and we're kind of expanding our notions. Like when we were learning linear transformations and parameterizations in particular, how parameterizations in some sense are an expansion of functions. I guess we didn't talk too much about that in this class. I think I was talking about it more in my Calc 2 class, of how parameterizations kind of expand upon these notions of functions and allow us to describe a broader array of curves. And so now we're kind of doing this in linear algebra with our notion of area, because what does this sign mean? What does it mean if I have a negative area, or if we get a negative value for a determinant? We'll just say the negative just means the orientation is the opposite. Sometimes we might call it a left-hand orientation. So let's take a look real quick. I don't want to talk too much about it. It's not terribly important for the scope of this course, but if you really like the geometry and kind of this notion of the pictures and like this notion of scaling, well, it kind of matters whether I want to consider U and V, or U to V, or V to U. We didn't talk about cross products. Unfortunately, we didn't have time. They are kind of coming up in this material. But if you've had Calc 3, maybe you've had cross products, and we kind of know not only does this have an area, but we kind of want a notion of orientation, meaning a notion of like the way we are naturally kind of curling around this. And it follows what's called the right hand rule. So if you use your right hand and you put your index finger along the first vector and then your middle finger along the second vector. So here's my U, my V is along my middle finger, and then my thumb is going to point straight up. The other way you'll see this is just by curling your fingers. So if you kind of curl your fingers from U to V, my thumb is pointing straight up. And so this is what we mean by a right hand orientation. And that positive sign just means that we are pointing upward. That's our area element, so to speak, or our area vector can be given a sign with an upward orientation. If we flip the order and do V to U, we will get a downward orientation. So we always follow the right hand. Actually, so I should change that. It's technically not left hand. It's just the opposite. It's just curling in the opposite direction. So if we went from V to U, now I have to flip my hand upside down. And if I go V on my middle finger, U on my index finger, or V on my index finger, U on my middle finger, my thumb is now pointing downward. And so that'll give us a negative orientation. Okay, so a lot to talk about there in terms of the formalities now with all of this. And so some things we're going to need. One, we're going to need to expand it to higher dimensions. And then we're going to need to understand how determinant plays with all of these other structures we have with matrices: inverses, transpose, multiplication, addition. So let me see. So do we want to expand on anything else? Let's go up through the formalization of the computations. And then we will keep going back to that example probably. It's easier to see in 2 dimensions some of the geometry of why we're measuring the things we measure, why we have this signed area. And then we can kind of talk about what's going to happen with row operations, all that kind of stuff. Okay. So, generally, for an n by n matrix, the determinant is calculated as follows. So the first thing we want to introduce, so if we have a matrix that is n by n, then we describe the minor Let me double check on that. I think that's the notation that the book uses. I want to be consistent with the book. There's different notations that people use. Determinants, cofactors. They first describe the minor, which they just write it out as minor. So minor AJ is the determinant of the matrix formed by removing row I and column J. Well, we only know how to take determinants for two-dimensional matrices at the moment. So at least we can describe what a minor is. This is also a little weird notation from the book. Sometimes when people describe the minor, they also aren't talking about the determinant. They're just talking about the matrix itself. So whether a determinant is involved, you kind of got to get from context. But for example, if we have a matrix, let's use a 3x3 now. And 1, 0, 3, 4, minus 3, 0, 1, minus 1, and minus 1. Then our A11 minor, what we do is just look at, we kind of eliminate row 1, eliminate column 1, and then the matrix that's left is often described as the minor matrix or the 1-1 minor. And then if we need to take a determinant, now we know how to take a determinant. So we're going to have 3 minus 0 equals 3. The minor of A, let's say, let's do 2, 3. So what are we doing here? We are taking the second row out and the third column. So 1, 0, 1, and minus 1 remain. Take the determinant. We've got negative 1 minus 0 again will give us a minus 1. The other thing we want to keep track of is this sign of the permutation. And this kind of ties back into this, well, am I doing U to V or V to U? And so each term is going to kind of have a sign. And the cofactor, let's say the ijth cofactor of A is the signed minor ij. Signed ij minor of A. Where the sign is determined by just minus 1 to the I plus j. So for example, again, we often write it as just cof A of, let's do 3, 2. So we're just going to have a minus 1 times 3 plus 2 Now, this one is important. Whenever we write the cofactor, determinant is always implied with this guy. So we do need to take our determinant of 3, 2. So we're eliminating the third row, second column. We're left with 1, 4, 3, 0 in our columns. We take that determinant, we're going to get 0 minus 12. And then we have minus 1 to the 5th. And so what are we going to get? A positive 12 from that guy. So for our matrices, for an n by n matrix, sorry, it has to be n by n, has to be square. The determinant of A is given by what you're going to do is to take the sum of all of the cofactors of A, where the sum is going to be taken along various cofactors that we expand for a given row or a given column. So mathematically, it's going to look like this. It's going to be A11 times the cofactor, the 1, 1 cofactor, plus A12 times the cofactor of A12. And you're going to add them all up. So A1n times the cofactor of A1n. So of course, if we wanted to write this, some of our j's, and then we can build upon that. So now we can essentially inductively define this is a generic formula for n by n. Of course, how do I get to a 4 by 4 matrix? Well, in order to get to a 4 by 4 matrix, we have to know how to take determinants of 3 by 3 matrices. In order to compute determinants of 3 by 3 matrices, we have to know how to take determinants of 2 by 2 matrices. And those ones we know how to take. So from these 2 by 2 matrix determinants, we can build up to higher dimension 3, 4, 5. So, example. Let's give a matrix. Let's give something fairly easy. Let's say 1, 0, minus 2, 3, 4, 5, minus 1, and let's see, let's say 7. I haven't used 7 yet. So what do? We start with 1. That's our 1, 1 coefficient, times, now we're eliminating row 1, 1. So we're at position 1, 1, and we're taking the 1, 1 cofactor. So times 4, 5, minus 1, 7. And we're going to be multiplying that by a negative sign, negative 1 to the 1 plus 1. Then we're going to add negative 1 to the 1 plus 2. So now we're moving on to second column. And now we're going to look at the 1, 2 cofactor. So we're going to have 3 minus 1, 5, and 7 remain. And then that one, I forgot my coefficient, so we'll have a 0 out front times that, plus minus 1 to the 1 plus 3, times our coefficient times now the 1, 3 cofactor. So we'll have 3 minus 1 and 4 minus 1. So if we reduce the problem of finding a 3 by 3 determinant down into some arithmetic with 2 by 2 determinants. So now we got to compute each of these. Nicely enough, the minus signs are always going to alternate. So if you start at 1, 1, negative 1 squared is going to be 1. So we're just going to have 4 times 7 minus 5 times minus 1. This one will be a negative, but it'll be 0 since it's 0 times something. Always nice when we have zeros in a row or a column for determinants. And then we're going to have a plus. We'll have negative 2 times the determinant of this guy, 3 times minus 1 minus 4 times minus 1. So be mindful of all those minus signs. We're going to have 28 plus 5. We're going to have plus, let's see, negative 2 times negative 3 plus 4. So we just positive 1. And now all in all, what do we get? 33 minus 2 is going to be 31. And so the theorem still holds. The first theorem we learned, we want to interpret determinants as the signed area. So if we were to plot these vectors, 1, 3, 1, 0, 4, negative 1, and then minus 2, 5, and 7, if you were to plot those on a 3D grid and then make a parallel pipette, so it's going to look like a prism out of those 3 vectors, and then compute the area, you'd get 31. So this process, this is known as Laplace expansion. So where we are essentially expanding out our determinant calculation in terms of cofactors and subdeterminants. So if you ever see the phrase use Laplace expansion, that's what we mean. Okay, so some properties of determinants. There's a lot of different things we can do. Nicely enough, they don't largely affect the determinant. So let's see. Yeah. Let's do. I'm just trying to think of what order we want to go through these. I'm not going to give any of the proofs to a lot of these. The proofs are in the book. They can get kind of technical. We're not going to have time for a lot of these proofs. Is it positive 2? Did I miss a minus sign somewhere? Because we got negative 3, but this one's a positive 4, right? So then that minus 2 is still negative. And then that sign is negative. So I think it's minus 2, yeah. Let me know if I make an arithmetic mistake. Okay, so let's kind of start listing out some of these theorems. I don't want to do them too rigorously because, as we kind of just saw, we saw the process of how to compute a determinant, and we actually have a little bit more freedom with how we can do that. So let's give some theorems that the determinant of a matrix is equal to the determinant of the transpose of the matrix. Hopefully that's not too counterintuitive. As I've kind of mentioned, geometrically, what's going on there? Well, it's kind of like, are we interpreting a matrix as row vectors or column vectors? Right here, the column vectors turn into the row vectors with the transpose. And so if you can kind of imagine that if it doesn't matter between row vectors or column vectors, then these two should, of course, be the same. The area spanned by the column vectors here is going to be the area spanned by the row vectors here. So it doesn't matter if we take a transpose. The other theorem we have, actually, let's get into elementary matrices first. And products. So other properties. If we have two matrices, then the determinant of a product of matrices is the product of the determinants. Likewise, so determinants of elementary matrices we've had, so type 1, we said Pij was switching the rows and columns, or switch. This was our rows, I and j. If we act on the left, if we have multiplication by this matrix on the right, it'll switch the columns I and j. We had the multiply a row by a scalar. And then the one we use most often with row operations is probably this add a scalar multiple of row I to row j. So the determinant if we switch two rows or two columns, determinant is -1. The determinant of multiplying one row by a scalar is just going to be that scalar. And then the determinant of taking a linear combination of rows and replacing one of those rows is just 1. So let's interpret this a little bit about what's going on. With our 2x2 matrices, so let's bring up our 2x2 computation again. We showed that the determinant is A times D minus B times C. So now the transpose should make sense, right? It doesn't matter if we take a transpose. We're still doing that computation in the same order of a 2x2. Play a little bit of play around with 3x3s if you'd like to kind of see that in action. But again, geometrically, it should make sense. As I was saying, the rows and columns essentially form the same size of parallelepiped. But what's going to happen if we actually switch the order of the columns? So if we have like BD over here and AC over here, that's actually going to just bring out a negative sign. And what do the negative signs mean? Negative signs just mean we're switching orientation, right? This is what it means. So the matrices not only encode our vectors, maybe V1 and V2, or if you want to interpret it as columns, you could have U1 and U2, or as rows versus columns. Right, we often put our basis vectors in column vectors. We could just as well put them in row vectors. And well, what does changing the order do? Well, we keep the same bases, but now what we're doing if we change the order, if we just flip two rows, we're essentially changing the orientation. Right now, you kind of want to interpret this as the ordered V1 to V2. Whereas like here, if we wanted to find our determinant, we chose U as our base. So it'd be kind of like having U and then V. If we change the order, what did we say? If we go V to U, what's the orientation do? It flips by a negative. So we get a minus sign. So that's all that minus sign means. It's why you should kind of at least intuitively understand why switching two rows or two columns is going to give you a negative sign. Likewise, if we scale one of the vectors, if I have my u and v, that's going to make a certain area. But what happens if I take one of these vectors and then stretch it by a factor of t? What's going to happen to the area? Well, we're going to get that many times the area. So our determinant is going to scale by that factor. And then number 3, this one's actually kind of interesting. You got to think about it a little bit. So remember, if we have a basis, we can create new basis elements or change our basis elements by taking a linear combination. Namely, this is like an elementary linear combination. I just take scalar multiple of one element of one row, one basis element, and then add it to the other one. And then we're replacing that other one. So the information from row J hasn't been lost. We've just taken the information from row 1, which is already in the matrix, and used it to modify what row J looks like. We haven't changed the overall information in the matrix. Kind of like here, we kind of have. We've actually changed one of the rows. We have a completely different row now, but it's just scaled by a multiple. So in some sense, we changed the information in the matrix by a little bit, a measurable amount. Here, we didn't change the information in the matrix at all. We just changed the order of the information. So that just changed the minus sign. It didn't change the overall size of the area. It changed our orientation of the area. And so that's kind of what you want to think here. Here, we keep the same orientation. We have all the same vectors in all the same order. We are just kind of taking some information that's already used in one vector and then throwing it in along with a vector, rj. And so we're not actually changing the size of the parallelogram. So all of those have that given determinant. And now this allows us to use this previous theorem, the fact that our determinant is multiplicative, to get some information about elementary row operations. Namely, if we take a multiple of that, so A is an n by m matrix, and B is the row reduced, let's call it the reduced row echelon form of A, then we know that B can be obtained by A by performing a sequence of row operations. So think of, first I take a scalar multiple of row 1, add it to row 3. Then we take a scalar multiple of row 1 and add it to row 2. In other words, if we keep track of our scalar operations, we can actually compute the determinant of a matrix by just computing the determinant of the reduced row echelon form and then modifying it by the elementary row operations, by the determinants of the elementary row operations that we perform. And those are just nice scalars, right? It's always 1, -1, or maybe a scalar multiple. So since most of these determinants are 1 or -1, it gives us some headway in terms of computing determinants, especially for larger matrices. So we'll see an example of that in 1 second. Let's list one last thing. Actually, here, so what do we get from all of this? There's a few things we can get. So let's see, some other properties of determinants. So proposition. Let's say that the determinant of A can be found by expanding, so doing Laplace expansion about any row or column. So far we've determined this Laplace expansion method only by expanding about the first row. But with this other information, we can kind of realize that it actually doesn't matter which row we expand about. Well, so first of all, we can do a row or a column because it doesn't matter whether we take A or the transpose of A. So if we are doing these matrix calculations, instead of expanding 1 times the subdeterminant, 0 times that subdeterminant, 3 times the other minor subdeterminant, well, if I take a transpose, that's going to move this row or the column to the first row. So I could have just instead started it and done the column expansion with Laplace expansion. But the other thing we've learned is, well, now I can switch rows, and all that does is multiply the matrix by a minus sign. Well, I could switch the rows, now do either a column or a row of one of the middle or the third rows if we wanted to switch it to the first place or to the first column or the first row, then do Laplace expansion, and what's going to happen, it'll just be negative of that. And it turns out, well, we're going to get the same matrices. All that's going to do is switch the signs in front of them. So if instead of actually switching the rows first, let's just keep the matrix as it is and then do our Laplace expansion down a given row or down any given column, it'll give us the same result. It'll give us the same area, same determinant. And then the last one that's going to be useful in conjunction with all of these is that if A is a triangular matrix, either upper triangular or lower triangular, then the determinant of A is the product of the diagonals. So that's going to make the computations really easy. In other words, our determinant of A is just A11 times A22 all the way down to the lower right corner. And let's see, I think that's about all of them. We've got one more. So our other proposition is that if I try to take a determinant of the inverse of a matrix, it's just the multiplicative reciprocal of the determinant of that matrix. This one's fairly easy to show since I know that A inverse times A gives us the identity. The determinant of the identity is going to be 1. So that forces that these determinants are multiplicative reciprocals of each other by the multiplication property. Any questions? So it looks like it's about 12:55. What we want to do is maybe do an example. So there's different ways we can compute these determinants now. I'll just introduce the example. I don't want to go through it all right now. We can start off tomorrow's class with it. But if we have like a larger matrix, so here's a 4x4, it's looking fairly difficult. So common things I look for if you have to compute a determinant, it's nice when there's zeros in the row or column. As we kind of saw with our 3x3 matrix, any of the minor determinants that we have to compute, well, if the coefficient in front of that is 0, we don't even have to compute it. So it's going to save us some time. Unfortunately, with this one, there's no zeros in it, right? So maybe what we want to do is maybe do some elementary operations first. If we do some elementary row operations and maybe get a bunch of zeros in these rows, then when we expand out our determinant, it becomes a lot easier. So that's going to be our process. We'll do this tomorrow. We'll go through do some elementary operations. And reduced row echelon form is actually overkill by our previous theorem in terms of diagonal matrices. If we just get it in row echelon form, and maybe not even with strictly having ones on the diagonal, but row echelon form, we want, says we're supposed to have ones on the diagonal and then zeros below those. If we can just get it to a point where it's zeros below the diagonal, then finding the determinant is really easy. So maybe we'll go through that method. We'll do that tomorrow. And then as well, we will start into our applications, methods for finding inverses. So we just saw at least that the determinant of the inverse is the multiplicative reciprocal of the determinant. But we can actually expand upon that a little bit and now apply that to actually computing inverse matrices. And then we will talk about Cramer's rule as well. So that'll be Wednesday. Any questions?